Yes, that's what I said. If you write the series expansion at a point, and if it converges at a point, then it converges in an interval. Okay.
No, sir.
If the series converges at a point, then the series converges in an interval. Okay.
Like this.
Yeah, that means you need the differentiability not only at one point, you need the differentiability in a neighborhood of that point. These are the necessary conditions for writing the Taylor series. Because you write the Taylor's theorem, you are going to write the remainder term not at the point. You are going to, the remainder term is going to be around the point, right? That is the lies on the line joining the point A and X. Okay, that means it can be anywhere. So that means that the n plus 1th derivative exists at all points in the interval. Look at the hypothesis of the Taylor's theorem. Yeah. Any other questions?
Yes sir.
Yes.
सर आपने लास्ट क्लास में थ्योरम 1.6 करवाई थी. सर उसके प्रूफ में आपने बोला था कि LH contains only one of the skew diagonal elements.
No, not the LH complete LHS. See what I did there is, see you have the series CK, right? So
yes,
this
sir.
mod CK, if you take, okay, this one contains the elements of the skew diagonal. Okay, so the elements of the skew diagonal comes like this. You know, so this diagonal elements, no, they are the skew diagonal elements. But if you take the sum of these from starting from k equals to 1 to say k equals to 1 to n, this is 1 to n. Okay, then k equals to 1, this is k equals to 0, this is going to be the case, the first one. K equals to 1, this is k equals to 2, this is like this. Okay, so this basically covers all the elements. The sum here covers all the elements. Okay, so let us yeah, so let us start with today's lecture. Yeah, mute yourself unless you are asking a question. So who are the
sir?
Yes.
सर नोट्स में आपने बस ये लिख रखा है कि LHS contains only one of the skew diagonal elements.
Yeah, that was a small mistake in the notes. So I revised it. I will write it once again. I will share it.
Okay, sir. Okay.
Okay, so the Legendre equation. So this is the Legendre equation is the equation which is like this. So it is 1 minus x square into y double prime minus 2x into y prime plus p into p plus 1 into y is equals to 0, where p is a scalar. Where p is a scalar. So you see that this equation is also written in the form of this form. I will use it later. This is the form which is called the self-adjoint form also. Okay. So both these things are the same, and so this is called the self-adjoint form. I'll tell you when it comes what is the meaning of self-adjoint. And this in the normal form is the what we have been writing, that y double prime plus a1 x into y prime and a2x into y double prime. Okay, so this is one function, and p into p plus 1 upon 1 minus x square into y is 0. So this is normal form. So if you see in the normal form, then you have the coefficients. A1x is from our earlier theorem that we proved. A2x is going to be p into p plus 1 upon 1 minus x square. Okay. So now you see that this a1 and a2 are real analytic functions around 0 with positive radius of convergence. That in fact the radius of convergence is going to be 1, because this 1 by 1 minus x is power series with radius of convergence 1. So let me tell you a couple of applications of this Legendre equation. So this is a very important application. It is an equation coming from the mathematical physics. Okay. So this is Schrodinger equation. So I'll tell you what this Schrodinger equation comes. I won't be able to write it here because it is a partial differential equation. So the Schrodinger equations. So these equations actually come in the quantum mechanics. Okay, so the quantum mechanics. Okay, so in the study of one electron atom, so you can, interested students can look at these things. So the study of one electron atom, but basically the Schrodinger equations are used for many applications in quantum mechanics. Not only this is one such study. So the Schrodinger equation is actually a partial differential equation, and that partial differential equation can be reduced in some special cases. Okay, in some special cases, in the special cases of that Schrodinger equation is Legendre equation. Okay, is Legendre equation. So when you solve, when you are trying to solve any real world problem, you won't be able to solve the model that comes straight away. You will have to do some stitching job around that. So that is, you have to assume that some special conditions, and those special conditions will lead you to a nice differential equation. And if this nice differential equation has a solution, so you can assume that the given real world problem, which you modeled into an equation, into a partial differential equation with bounded conditions, also has a solution. So this is one equation, one application of this, and also there are, the study of the study of flow around around the outside, okay, outside of a gas puff. The gas puff means that you see if the gas is coming out of a nozzle, okay, that is a puff is formed. Okay, so what is the flow around the puff, okay, of hot gas, okay, rising through air. So these are some of the mathematical models where you have where you get the equations, which you won't get the equations with equation directly, Legendre equation, because these models are a three-dimensional models. So if you look at the gas puff, it is going to be a three-dimensional model. There will be x, y, z, three variables. So what you get there is a partial differential equation. But that partial differential equation, under some special conditions or special assumptions, so it reduces to the Legendre equation. So that is the importance of the Legendre equation. And also I will tell you about some special polynomials that will come as solutions of Legendre equation, which are used in many of approximation theories. Okay, so going back to this, I have the equation a1x, which is minus 2x by 1 minus x square, and a2x is equals to p into p plus 1 upon 1 minus x square. So both these things are real analytic. Okay. Around 0, around the point x equals to 0, with the radius of convergence to be equals to 1. Okay. Or the validity of this power series is valid from minus 1 to 1. Okay. The validity of the power series is valid in the interval minus 1 to 1. Right. So if you write this equation in the right, you can write what the a1x is going to be. A1x is minus 2x times you can write the series in the form of x power 2k. This is basically the 1 upon 1 minus t. Okay, 1 upon 1 minus t is going to be 1 plus t square, like that. Now replace t by x square. Similarly, the A2 is going to be P into P plus 1 to x power 2. Okay, so both these things are valid for mod x less than 1. Both these things are valid for mod x less than 1. So we assume that the solution y to be the form of ck x power k, and then try to find what these ck's are. Okay, so we are not going to use this form of a1 and a2. We just check that these are real analytic functions. Therefore, we can get a solution by the Taylor series method or by series method. Now we are sure that the solution will come. Now we will go back to the equation and then try to substitute this y and try to get the solution or the coefficients. So if y is that, then we write minus 2x into y prime. That is going to be the sum of minus 2k ck into x power k. Right? So differentiate and multiply by 2x. That x power k minus 1 goes away, it becomes x power k. And this is for, we can write from k equals to 0 to infinity, though k equals to 0, it is 0. Similarly, the y double prime, we have, can write k equals to 2 to infinity of k into k minus 1 ck into x power k minus 2. So this is, I can rescale it, okay, rescale it to get k plus 2 into k plus 1 into ck plus 2 into x power k. And in the equation I have 1 minus x square into y double prime, so I need minus x square into y double prime. So this is in the first equation, if I multiply, I get k into k minus 1 to ck into x power k. I can write k equals to 0 to infinity, because anyway k equals to 0 and 1, it is going to be 0. I can write everything in the form of that. So these are the terms that I have, right? So if I write what is the equation now? The equation is going to be y double prime minus x square into y double prime, right? That is 1 minus x square into y double prime minus 2x into y prime plus p into p plus 1 into y. So if I substitute everything in this, I get k equals to 0 to infinity. Y double prime I will take, because I need x power k, so I will take the first, this one. Okay, take this one. So I get k plus 2 into k plus 1 into ck plus 2. Okay, minus x square into y double prime we take from here. That is going to be minus k into k minus 1 into ck, and minus 2xy prime. So we take 2xy prime. This is minus 2k ck plus p into p plus 1, the whole thing multiplied by x power k. Okay.
So third line में एक minus.
Third line में
Summation k equals to 0 to infinity minus k
into k minus 1, yeah, minus 2k into ck plus p into p plus 1 into ck, yeah, ck,
yeah.
yeah. So this equals to 0 implies the following relation, that is k plus 2 into k plus 1 ck plus 2, right? And the ck terms we can write all of them together, and we can do some simple algebra here. We can write this as p plus k plus 1 into p minus k into ck. So this is going to be equals to 0. So this is true for all case, because k equals to 0 to 0, 1, 2. Right, so this gives us a recurrence relation. Okay, so this gives us a recurrence relation. Let us write what this recurrence relation is going to be. So this is ck plus 2 is going to be minus of P plus K plus 1 into P minus K upon K plus 2 into K plus 1 into Ck. So from here, this is K equals to 0, 1, 2, like this. So take K equals to 0. Okay, when I take K equals to 0, I get C2 is equals to minus P plus 1 into P upon 2 into 1 to C0. So C2 we could find in terms of C0, right? So similarly, if I take K equals to 1, I get C3. C3 is going to be minus P plus 2 into P minus 1 upon K equals to 1. So 3 into 2 into C1. So take K equals to 2, I get C4, right? So C4 is going to be K equals to 2 is P plus 3 into P minus 2 on 4 into K plus 1 into 3. So into C2. So from the previous step, I can write what is C2. So P plus 3 into P minus 2 by 4 into 3 to 2 into 1. Therefore, it becomes factorial 4 times P into P plus 1 times C0. Okay. Similarly, you can find C5. Okay. So what we found is that all the even coefficients C.
सर जो माइनस साइन है वो खत्म नहीं हो जाएगा क्योंकि हमने C2 की वैल्यू ऊपर माइनस की नेगेटिव थी तो नेगेटिव नेगेटिव कट हो जाएगा C4 पॉजिटिव आएगा.
Yeah, so it becomes plus. Okay, thank you. So the what's happening here is that all the C2Ks, okay, you can find something times C0, and C2K plus 1 you can find some constant which depends on P times C1. So that's how we can find the solution, right? So we can write these terms together to write a solution in this form. Therefore, the Yx becomes now solution C0 into 1 minus whatever we found there, plus 1 by factorial 2 to x square, and like this, all the even terms you can write, plus C1 times x minus P plus 2 into P minus 1, okay, divided by factorial 3 to x cube. So this is what we can write as C0 into the phi1x plus C1 to phi2x. Why I wrote phi1 and phi2 is that these two are the functions which are linearly independent, because you can see that one is having the coefficients in the form of x square, x power 4, and the other one as x cube. And so, but it's not difficult also to write what the Wronskian of these functions is. The Wronskian of phi1, phi2 at a point x. So basically there is a theorem which comes in the second order equations to show a formula that is the Wronskian of any two solutions of a differential equation is going to be the Wronskian of phi1, phi2 at any point. So you can take at any point, okay, times some exponential of integral of this a1. So this you can try to prove this relation. This is called Abel's formula. It's not very difficult. You can see the basic book on second order equations. Just writing the equation satisfied by phi1 and phi2, and then subtract them, and then you can write what is the Wronskian. The Wronskian is basically the determinant, right? So it is phi1, phi2, phi1 prime, and phi2 prime, the determinant of this. Okay. So of at any point you take x0 equals to 0. Okay, so phi1, phi2 times at 0 times exponential of 0. So this is something which is never 0. So this basically this formula implies that the Wronskian is either always 0 or never 0. Okay. Right. So if Wronskian is 0 at the point 0, then the Wronskian is going to be 0 everywhere. So if you see this one for this equation, P1, P2 at 0 it is going to simply look like this. Right. So this is not 0. So this shows that these two Phi1 and Phi2 are linearly independent. I mean, there are many ways to show. It's not really you need to use the Wronskian. You can write Phi1 and Phi2, and then write Phi1 is not a constant multiple of Phi2. So suppose if yes, then you take different values of x to say that C1 is identical equals to 0. C1 and C2 are identical equals to 0. Okay, so Phi1 and Phi2 are linearly independent. Okay, so it can be shown directly also. Can be shown directly. Try this. Okay, so this is these are the linearly independent nature of these functions. And another thing is that anyway we know that there is the solution of this equation. Okay, the power series solution of this equation converges, but you can find what is the radius of convergence by looking at the recurrence relations. Okay, so we look at the recurrence relation here. So this tells us what should be the what is the convergence of this solution. Okay, what is the radius of convergence of this solution? So we write the if you look at the first Phi1. Okay, so this is the Phi1 is coming from this C to C4. That means this adjacent coefficients in the series of Phi1 are related by this recurrence relation. Similarly for the C2. Okay. So to find the radius of convergence, okay, so we simply use the recurrence relation to write Ck plus 1 by Ck, Ck plus 2 by Ck. That is how the adjacent coefficients are related. So P plus K plus 1 into P minus K 1 K plus 1, right? So now you can see that this actually is a quadratic on the, you can take K square as a common factor, and then you see that this actually goes to 1 as K tends to infinity. So I leave this as an exercise to you. It is not difficult. You can do it yourself. Take the K square as a common factor from the top and as well as the below. So either P by K goes to 0 and this becomes 1 and this goes to 0 and this is similarly, right? So on the absolute value, everything goes to 1. Okay. Right. So therefore, the radius of convergence R is 1. So the solution converges in the interval minus 1 to 1.
Hello,
Yeah.
sir.
Yes.
Sir, here P is any function or constant?
P is a scalar, right? That's what I said. P is a scalar. P is a scalar, which is a real number. That's what I said in the beginning. Right? P is a scalar. P is a real. Yes.
So Ck is any constant here?
Which one? C?
Ck.
Not any constant. We are finding, I mean, we are assuming that the CK is the sequence of real numbers. And we will find the CKs by substituting that function in the equation. So finally, we found that CKs are satisfies the recurrence relation. And then we found all the CKs in terms of either C0 or C1. Of course, C0 and C1 are arbitrary constants, right? That's what I mean to say that this is how the general solution looks like. So
okay, sir.
I can take C0 to C1 to be arbitrary constants. I can take C0 equals to 0 and C1 is 1, or the vice versa. If you take both of them 0, that is also a solution. 0 is also a solution.
We can find C0 and C1 also.
You cannot find, they are arbitrary constants, right? Because the second order equation should have two linearly independent solutions.
Okay, sir.
So it should have a general solution. So this is the general solution. So I can take C0 and C1 to be arbitrary constants. In particular, you can take 1, 0, 0, 1.
हेलो सर.
Yes.
सर ये बीच में आपने लिखा है -2x. सर -2x वाइड -2x वाइड एस है, तो k वेरी फ्रॉम 0 to infinity कर रखा है, वहाँ 1 to infinity नहीं होगा क्या?
0 में क्या होगा अगर 0 लिखूं, even if I write 0 there, right? Even if I write 0 there, what happens?
हाँ सर, फर्स्ट लाइन k वेरी फ्रॉम 1 to infinity.
Now I write what k equals to 0 to infinity. Expand it. Expand now. K equals to 0, it is going to be 0 plus k equals to 1, right?
Okay,
so किसी को भी 0 add.
Okay, sir.
Okay, so this is the Legendre equation. So like this, there are many equations that come from the mathematical physics. There are Hermite equation, Legendre equation, and equations like that. So we'll do some of them. Some of them be the similar type of Legendre equation I gave in the exercises. You can see that. And some other equation, one important equation we'll see later, that is the Bessel equation. Okay, so now the importance of this Legendre equation is the Legendre polynomials. So what are these Legendre polynomials? So Legendre polynomials are, if you see the equation, the coefficients that I got, okay. So if I take say p equals to 1, okay, then C3 becomes 0. See that? When p equals to 1, if I take C3 becomes 0. Once if C3 is 0, from this relation, from this recurrence relation, implies that all the C5 is 0, C7 is 0, all other coefficients are going to be 0. Therefore, if C3 is 0, I'm going to get here, the second solution is going to simply have the linear polynomial. Okay, so it simply has only x. Similarly, if I take p equals to 2, C4 becomes 0. Okay, p equals to 2 if I take, and p equals to 2 if I substitute here, then C4 becomes 0. So once if C4 is 0, right, C6 is going to be 0 from the recurrence relation. C6 is 0 implies C8 is 0. So all of the further coefficients are going to be 0. Therefore, if I look at the first solution, phi1 here in this case, it will have only C0 plus C2 into x squared. Okay, so these are called the polynomials. That is, when I take say p equals to 0. Okay, so when we take p equals to 0, this implies that p1x, okay, is going to be simply a constant, C0. And similarly, when I take p equals to 2, I get the p1x, okay, is simply going to be a constant like this, C0 plus C1 x squared. Okay, of course, C1 I can find once if I choose C0. Like this. Similarly, these are the even polynomials. Similarly, if I take p equals to 1, I get p1x is going to be, so this is C2x squared, C1x, and p equals to 2 applies, I get p equals to 3. So I get the, so this is p2. P2 is going to be the, yeah, P2 is going to be C1x plus C3. So what we are seeing here is that when P is, if P belongs to, okay, this, I'm getting, that is, if P equals to N, p equals to n, then one of the solution is polynomial of order n. Is a polynomial of order n. Okay. So this these polynomials are called the Legendre polynomials. So these polynomials are called the Legendre polynomials. Legendre polynomials. Okay. So you can write in the standard form by taking C0 equals to 1 and C2 equals to 1. Sorry, C0 equals to 1 and C1 equals to 1, what is written in the notes. Right. So there is also a very these are denoted with P and X. Okay. So a general formula is given for this. This is by choosing the constants. Okay. So d power n by dx power n into x square minus 1 power n. Okay. So these constants are chosen in such a way that Pn at 1 is going to be 1. That's the idea. Okay. So with this normalization constant, this constant is chosen 1 by 2 power n into factorial n. The constant is chosen in such a way that Pn at 1 becomes 1. Okay. So these equations, these polynomials, okay, are called the Legendre polynomials. And it is, you can see here, you can show that this is actually a polynomial of degree n. Why is that? You look at this x square minus 1 power n, it's a binomial expansion. The highest order term is going to be x power 2n. X power 2n, when you differentiate n times, it becomes x power n. Okay, is polynomial of order n. So that's not difficult to see. And then you can expand it and then see by you can in fact show that this Pn satisfies the Legendre equation. Okay, this Pn's satisfy the Legendre equation. So you can substitute in the equation. Okay, Pn satisfies Legendre equation. And you know because now you know all the solutions of all the polynomial solutions of the Legendre equation. Therefore, this has to be the solutions. So checking this is also not difficult. You can write, you can differentiate this twice. Okay, Pn double prime. Anyway, it is in the form of two derivatives, and then use some simplifications to some trivial simplifications to show that it actually satisfies the. You can substitute this in the equation. So this is about the. There are some problems on the Legendre equations. You can see. You can try to do it in the. I gave these problems in the end of the notes. You can try to do these things yourself. And you can ask me any questions that you have before we go to the next topic. Do you have any questions?
Sir, I didn't get this Legendre polynomial.
What?
This P and X.
What is that?
So I didn't get that. What actually this is?
You didn't get?
Yes, sir.
Okay. So when you take the Legendre polynomials with the, I told you what is the Legendre polynomial of order 1. Okay, that is going, order 0 is this, and similarly the Legendre polynomial of order. Okay, so this is going to be 1 minus 3x square, and phi 3 is you can write as right. So third. Yeah, so this is second order. So you have the, sorry, this is phi 3, third order. So phi 2 is going to be, no, this is phi, this is phi 0. Okay. So the phi 1, the first order one. So that is x. And phi 4, right? So you can write these things from I'm writing all wrong. So the Legendre polynomial of order 0. Okay, so that is phi naught, or I can write the polynomial of I'm already using the phi1 and phi2 for something else. So when I take p equals to 0, okay, one of the solution is simply the, okay, that you can see from the coefficients. Is that clear? At least that part is clear. When I take p equals to, this comes when we take p equals to 0. Okay, this you see that from the recurrence relations, right?
Yes, sir.
Yeah. Okay, so when I take p equals to 0, I get p naught equals to 1. So this is a solution. So similarly, when I take p equals to 1, the other side, that is the second linearly independent solution, becomes a polynomial, and that polynomial is, I'm calling it as p1, which is x, of course by taking appropriate constant c0 c1. So this is also a solution. Similarly, when we take the p equals to 2, we get again a polynomial solution which is coming from the p1. Okay, so that is going to be, I call this as a second order polynomial, 1 minus 3x squared. Okay, all these polynomials, I want to have a generic formula for this. Okay, given n, I want to simply find what the polynomial, Legendre polynomial is going to be, without going to that infinite power series and substitute these things. So there is a generic formula. Okay, so the generic formula for Legendre polynomials, or a generic representation. Generic representation. That is this Pn for any n. Okay, for any n, I can write Pnx is what is given there, 1 upon 2 power n into factorial n into d power n by dxn of x square minus 1 power n. So you see that this is a polynomial of degree n. That is because this, when you write the binomial expansion of this, the highest order term is going to be x power 2n. And when you write d power n by dx power n, the n times if you differentiate, you get some x power n times some constant. So this is actually a polynomial of degree n. Okay, so it's a polynomial of degree n. So you may ask the question, why this constant is chosen? Why not some other constant? So with this constant, actually Pn at 1 becomes 1. That is the normalization constant. So the constant is chosen so that Pn at 1 is going to be 1. Okay, and we may ask the question, why these Pn's are in this form? What is the proof of this? Okay, what is the proof that these are the polynomials which we get from the series? So for that, you write, you can show that, okay, show that 1 minus x square into Pn double prime minus 2x into Pn prime plus p into p plus 1 into Pn is going to be 0. Assume that once we have shown this. So what does this become? This means the Pn is going to be in the general solution of that C0 phi1 plus C2 phi2, right? Right. So this implies that Pn is a solution. So this implies that Pn is C0 times phi1 plus C1 times phi2. You can see that? Yes?
Yes, sir. We can see.
Right. So once if you see this one, and when p equals to n, one of them is actually, when p equals to n, one of them is a polynomial, other one is a series. Okay. So either phi1 or phi2 is a polynomial. Therefore, this implies that either C0 or C1 is 0. Okay. Say for example, if I take even coefficients P2n, then it becomes C0 into P1 and C2 becomes 0. Okay, and we know that this is also a polynomial. Therefore, P2n is going to be equal to this. Okay, if I choose the constant to be exactly the coefficient of this P2n. So that is how this one can show that these PNs are actually solutions. So, but this is a very good exercise for a nice review of your calculus. Okay, the product formula, how you use this second derivatives to write the binomial expansion, and it's a nice exercise. You can try this. I don't know if I gave this as an exercise in the problems. Let me see. If not, you can try this as an exercise. I didn't give this, but you can try this. Yeah. So differentiate this. Yes. Yes.
Sir, how
yes.
Pn of 1 is 1, sir? Last phase. Sir, if you put x equal to...
I'm saying when I take 2n, right? So I'm taking 2m, say n equals to 2m.
No, sir. In last page.
Yeah. So when I take n to be the even numbers, right? I'm going to get even polynomial, right?
No, sir. I'm talking about last page.
Last step only I'm saying. When I take n equals
last
to
page,
2m.
Last page.
Last page.
Yes.
Yes, sir. Yes, sir.
What is that? Pn of 1 is
Pn
1.
Of, how did we get this, sir? Like if you put x equal to 1, it becomes 0, no, sir?
No, it doesn't become 0.
It should.
It should not become 0, right? That's why I said Pn of 1 is 1. Apply the product formula. You have the x square minus 1 is written as x minus 1 into x plus 1. Okay. You have to do this. These are the some nice exercises. You can try to do this. So coming from the calculus. So you see x square minus 1 over n. So what is this? This is n times derivative of x minus 1 into x plus 1, right? So apply the product formula on this. Then you see that the derivative each time is going to be either on this or on this. Okay. So
yes,
that is the reason why it is not going to be 0.
I thought we have to put diet x equal to 1. So
no, you can't put it.
Okay.
So use this cleverly to expand this one. It's not very difficult. Okay. Observe what happens for n equals to 1 and n equals to 2, and then write what is the product formula, right? So d square by dx square. It's all coming from the binomial, right? Binomial coefficients. So when you write d by dx of fg, you are writing f prime g plus g into f, g prime into f, right? So similarly, you write d square by second derivative of the product fg. Then you differentiate that form. Like that, you write the product formula for nth, and then see that it acts on one of them only. And when it acts on this one and then put x equals to 1, you are going to get 1 only, and the other one becomes simply 2 power n. So sorry, x power n and the power n here. Okay, so that is why it is not going to be 1. I should have ideally added these things as part of your exercises, but I didn't add them. But you can try. Otherwise, I will do it in the tutorial class. Try this before, and otherwise, I will do it in the coming tutorial. When is on? It's on Wednesday, right? I'll do it in the tutorial. But try to do these two things before that. Use your idea of the calculus to show that this satisfies this equation, and for the given formula, Pn at 1 is 1. Okay, Pn at 1 is 1. Okay. Any other questions? Okay, so the so far what we have seen is you have this equation in the form of a normal form, that is in this form, that is a1x into y prime plus a2x into y equals to 0. okay, where a1 and a2 are real analytic functions. Now we ask the question that suppose if they are not real analytic functions, then what is that we can do? Whether we can still apply the power series method. That means these functions a1 and a1x and a2x, they are singular functions. Okay? So they may not be analytic functions. Okay? So we try to look at the equations of this type. That is x square y double prime plus x into a1x into y prime plus a2x into y. Okay, so if you write this in the normal form, it looks like this: y double prime plus a1x upon x, okay, into y prime plus a2x upon x square to y. So these are the type of coefficients. So if we have something like this, okay, then what is the way to write the function? So the solution. So if you see that these are these functions now a1x, if a1x is a nice continuous function, okay, or a1x is a real analytic function around 0, and a2x is a real analytic function around 0, but a1x by x and a2x by x square are not going to be. They are going to have singularity at x equals to 0. Okay, so if a1, a2 are real analytic, we are only talking about real analytic solutions. Therefore, we assume that functions are real analytic. Okay, then a1x by x and a2 by x square, okay, have singularity at 0. Singularity at 0. Therefore, you expect the solution to also have a singularity. You expect the solution also to have. So we expect the solution also to have a singularity. To have singularity. Okay. So it is only an expectation. It may have, it may not have. We don't know. Okay. Therefore, we try to take the real analytic function ak x power k equals to 0 to infinity, where this r is some real number. R is a scalar. We don't know what this r is. So we assume that yx to be is of this type. Okay, yx to be of this type. If yx is of, can we find? That's the question. Can we find the scalars r so that, right? So can we find the r and this ak so that y is a solution? So this is the method due to Frobenius. So it is called the Frobenius method. So the idea is that since the coefficients has a singularity, so will have some singularity. Okay, but it's not necessary to have singularity in the solution, but it's only expectation. Therefore, you expect the solution to be the S. But R as a scalar, it can be, if it is positive, then there is no singularity in the solution. If R is negative, then there is a singularity in the solution, right? If R is negative, then the x power -1 negative coefficient will exponent will have a singularity at x equals to 0. Okay. Okay. So yes.
One question. So how this assumption is made by just knowing, by just expecting similarity? How this y and x to power r is coefficient multiplied?
That's it's only an expectation, right? It's only intuition. Calculus is about intuition only. Entire calculus is only an intuition. First, you need to have an intuition. So I am saying that when I have a power series, because there is a upon x here, you see that there is a division by x. Therefore, if I multiply the series by x power r, and when that is multiplied here, and that by x is there, so maybe probably that gets cancelled. That's the expectation. Okay, so that's only an expectation. So, or if you see this form of this, if I have x power x square here, I have to multiply and.
So your sound is cracking.
Square. Maybe they get some kind of nullification happens here for R negative.
So your voice is not coming.
We don't know the power x power r. Of course, I'm talking about only the x positive. It's all the things I'm doing for x positive. X power r, if I multiply by this, maybe I'm able to get. That's what the idea of the Frobenius is. And then he devised a method which is called the Frobenius method. You can have any idea, right? So you can have any intuition, but whether that intuition develops into a good one or not, we don't know. So this, most of the times it happens. There is a big controversy about the turbulence theory. Okay, so when all these aeroplanes, everything, all these things uses the turbulence, the theory of turbulence. So in the early 1902, 1903, someone who became a great mathematician and also a great fluid mechanics person, he used some assumptions. He had some intuitions how the turbulence actually behaves, and that became kind of a great assumption in the theory of turbulence. And then many things are done, but he could never give a theoretical proof for that. And finally, it was proved very recently. Very recently, it was proved that his assumption was correct. So when you assume something and then you do the things, you get the answer and you get the solution, you are happy. But you may not be able to prove the assumption. But Frobenius method has a strong basis mathematically. So not like a turbulence theory, but still you have the intuition and you have the how this solution behaves, and therefore I should try this kind of things. And then maybe that I can develop a theory out of it. That's what the research is. If you are successful in developing a theory out of your experiments, that's very good. Okay, so I'll stop it here.
Thank you, sir.